This is the start of Chapter 7. Chapter 7 is all about logarithmic and exponential equations. 7.1 is on exploring exponential models. So we'll start with exponential equations, which you're familiar with exponents at least. Logarithms are probably new. That'll start here in a couple sections. An exponential equation is an equation with a variable in the exponent. So we have had equations that have exponents, like y equals x squared. That is a polynomial, specifically a quadratic, but it is not an exponential equation because the variable, the x, is not in the exponent. So this is not an example of an exponential equation, whereas y equals 2 to the x is the variable in the exponent. First thing we're doing is graphing a couple exponential equations. So example 1 asks us to graph y equals 2 to the x. Y equals 2 to the x, we're simply going to make an xy chart. And plug in some values for x. Let's think about what our domain is, what we're allowed to plug in for x. We can plug in positives, or 0, or negative numbers. Exponents can be negative as well. -2, -1, 0, 1, 2 will typically be enough. I'm going to plug in 3 just for this first one so we can get just a slightly better graph. Plugging in -2, 2 to the -2nd. Negative exponents go on the bottom. That's 1 over 4. 2 to the -1st. 1 over 2 to the 1st, that's 1/2. Anything to the 0 power is 1. 2 to the 1st is 2. 2 squared, 2 times 2 is 4. 2 cubed is 8. And then we plot these points. We have the point -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. So notice my y values are getting bigger and bigger. I keep multiplying by 2. So 4 is going to give me 16.5. I'm already all the way up at 32. So exponential equations, they do grow very quickly. Also, think about, is there anything that would give me 0 for y, or a negative number for y? 2 to what exponent gives me negative? Well, there's not one. 0 gives me 1. Negative numbers still give me positive because you just move them down to the bottom. Even like 2 to the -100 is 1 over 2 to the 100. It's still a positive number. So we don't cross the axis. Technically, you don't even touch the axis, although it gets so close to it, it's okay if it looks like it touches it, and it comes up. Whoops. It looks like that. We get infinitely close to the x-axis, but do not cross it. Example 2 is similar. Y equals 2 times 1/2 to the x. Notice this again is an exponential equation because the variable x is in the exponent. Again, we're just going to make an xy chart, basic xy chart. Plug in a couple negative numbers, a couple positive numbers, and 0. Let's plug in the positive ones first, simply because they're usually a little easier. We've got 2 times 1/2 squared. 1/2 squared would be 1/2 times 1/2, or 1/4. 2 times 1/4 is 1/2. Plugging in 1. 1/2 to the 1st is 1/2. 2 times 1/2 is 1. Plugging in 0. 1/2 to the 0 is 1. 2 times 1 is 2. Plugging in -1, 1/2 to the negative first. Couple different ways you could think about it. Negative exponents get moved down to the bottom. So I have 1/2 on the bottom. I have 1 divided by 1/2. Dividing by a fraction is the same as multiplying by the reciprocal. So this is 2. So I have 2 times 2, which gives me 4. Or another way, maybe an easier way to think about this, is that's the same as 1 to the negative first over 2 to the negative first. Negative exponents get switched. So 2 to the first over 1 to the first. Either way, you get 4. If that's -2, now it would look like this. So now I have 2 to the second over 1 to the second. Well, that's 4 divided by 1. That's 4 times 2 is 8. And we plot our points. -2, 8. -1, 4. 0, 2. 1, 1. 2, 1/2. Notice again, I'm never going to get down into the negative numbers. It's going to get infinitely close to 0, but not cross. So you should not cross down. It should not look like that. You should get close to 0, but technically not cross it. Notice we have 2 different graphs here. Some of them will start low and go up. Some start high and go low. One is called exponential growth and one is exponential decay. Notice example 1, this is an exponential growth graph. This one is exponential decay. It starts high and breaks down to close to 0. The question is, how can you tell just looking at the equation if we are going to have exponential growth or exponential decay? So most of the equations start in this basic form, y equals a times b to the x. Now they might be translated or they might be flipped, but the basic form is y equals something times something else to the x. And we are going to have exponential growth if b is greater than 1. If b is greater than 1, if the number I'm raising to the x, not the number out front, but the number I'm raising to the x is greater than 1, then we have exponential growth. We have decay if b is less than 1, and technically b has to be positive. It can't be a negative number. We won't get into that in this video, but b should be greater than 0, and actually it can't be 1 either. If I have like 3 times 1 to the x, no matter what I plug in for x, 1 to any power is just 1 times 3. So I just get y equals 3. That's not an exponential equation either. So if b is greater than 1, we have growth. Less than 1, we have decay. So notice here b was 1/2, less than 1, that's decay. B is 2, exponential growth. An asymptote is a line the graph gets infinitely close to at its extremes. At one or both extremes. So as x gets very, very big or very, very small, is there a specific line that we get closer and closer to? So this first example, notice the line y equals 0. Draw it in this so you can see it. But this line right here, it gets infinitely close to, but doesn't cross it down here at its extremes. We get infinitely close to y equals 0. The asymptote of this line is y equals 0. If it asked what the asymptote was, it is y equals 0. Notice the second one is also y equals 0. That line right there, we get close to as x gets bigger and bigger and bigger. Exponential equations, unless they are translated, will always have an asymptote of y equals 0. We'll talk about what to do if we translate in 7.2. So again, asymptote, a line the graph gets infinitely close to at one or both of its extremes. Example 3, we are given 2 points, and we are asked to write an exponential equation passing through the 2 points. Lots of times I see students, they see 2 points and they automatically find slope. Don't do that. Exponential equations don't have slope. This is not a line. Instead, what we are going to do is we are going to start with y equals ab to the x, a times b to the x, and we are going to plug in one of the points for x and y. Let's start with the smaller one. So 4 for y would say 4 equals a times b to the first. Notice I want to solve for a and b. I want to figure out what a and b are. I've got 2 variables, a and b, so I need 2 equations. I need a second equation, which comes from plugging this in for x and y. 144 equals a times b to the third. And now there's lots of different ways you could solve this. You could substitute. You could solve for a and substitute that over here, solve for b, and then plug that back in. The way I'm going to show you how to do it is I'm going to divide this side by 4 and this side by a times b to the first. So I'm taking one equation and dividing it by the other. And usually when I divide both sides of an equation, I have to divide by the same thing. Not usually, you always have to. But I'm dividing this side by 4, I'm dividing this side by ab to the first. Well, those are equal to each other, so I am dividing both sides by the same thing, as long as a and b are not 0. Notice the reason I'm doing that, my a's cancel, a divided by a cancels, and b cubed divided by b, when I divide, I subtract exponents, I get b squared. 144 divided by 4 is 36. Square root of both sides, I would get b equals plus or minus 6. Remember we said earlier that b couldn't be negative. It has to be a positive number, so we don't need to worry about the plus or minus here. B is just equal to 6. Once I have b, I can plug it into either of these equations. I would go with the one with smaller numbers and solve for a. 4 equals a times 6 to the first. Divide by 6 and reduce. And write your equation. Y equals a, 2/3, times b, 6 to the x. And then the last types of problems we are looking at are story problems that deal with exponential growth or exponential decay. We are going to start with the basic y equals ab to the x. Notice if I plug in 0 for x, it would say y equals a times b to the 0, and anything to the 0 is 1. So if I plug in 0 for x, I get y equals a. So a is the starting amount, the amount when x is 0. B is what is called the growth factor. The growth factor, if it says in the problem that something doubles means we're multiplying by 2. So b would equal 2. Triples, b would equal 3. If something is breaking in half, b would be 1/2. Easy enough. The ones we tend to struggle with a little more, if it says something like increases by 10%. Well, we can't make b equal to 10 because that means we'd multiply by 10 over and over again. And b also shouldn't be 0.1 because b equals 0.1, that would be decay, and it's increasing, going up. So if it's increasing by 10%, what you need to do is think about, right now we have 100%, and I want it to go up by 10%. So each time we are going to have 110% of what we had the previous time. The 100% that we started with, plus the 10% that we're increasing by. So b would be 1.10 in that case. You do something similar if it says it decreases by a percent. If it decreases by 10%, that means we're starting with 100, we want to subtract 10%. So each time we are keeping 90%. We are multiplying by 0.9 over and over in that case. So a couple examples here. Example 4 says a population of bacteria starts at 500 and doubles every hour. How many bacteria would there be after 6 hours? If you're taking good notes there, you don't have to write all that down. Starts at 500, doubles every hour. How many after 6 hours? That'd be enough. Because I'm multiplying by something over and over again, that's why we have an exponential equation. It also tells us right in the problem. It's an exponential model. So we're starting with y equals ab to the x. Our starting amount goes in for a. We start at 500 and we are multiplying by, our growth factor should be 2. And the number of times we are multiplying by 2, if it doubles every hour after 6 hours, it will have doubled 6 times. And this will be a calculator problem. 2 to the 6th is 64 times 500. So 32,000. That's a lot of bacteria. Example 5 says a certain element has a half-life of 3 days. If there are 14 kilograms of this element right now, how much would be left after 22 days? Half-life, hopefully in a science class, you've learned what a half-life is. If not, half-life is the amount of time it takes for the element to break in half. So like for this example, if we start with 14 kilograms, so time is 0. Right now we have 14 kilograms. After 3 days, we would have half that. After 3 more days, it would break in half again. We'd have 3.5 kilograms. After 9 days, it would break in half again, and we'd have 1.75, and so on. How long it takes for the element to decay by 1/2. So again, we're starting with y equals 8 times b to the x. Notice each time, every 3 days, it's breaking in half. We're multiplying by 1/2 over and over again. A is the amount we start with, in this case 14 kilograms. B, we are multiplying by 1/2 over and over again. And x should be the number of times it breaks in half. And we want to know how much would be left after 22 days. Well, it's not 22 because it wouldn't have broken in half 22 times. Think about if this said 21. If this said 21 days, if it breaks in half every 3 days, after 21 days, wouldn't it have broken in half 7 times, which we would get by doing 21 divided by 3. So our exponent, instead of 21 divided by 3, is 22 divided by 3. And now it's a calculator problem. 14 times 1/2 to the 22 over 3 power. Uh, 0.087 kilograms. And our last problem here says you buy a car for $18,000. This value goes down by 11% each year. What will the car be worth after 7 years? So again, we're starting with y equals a times b to the x. A is the starting amount. B is the growth factor. It's decreasing by 11%. So we start with 100% minus 11% gives me each year we are keeping 89% of its value, 0.89 to the 7th. To the 7th because it goes down by 11% each year, so after 7 years it will have gone down 7 times. We're taking 11% off 7 times. And again, these stored problems are almost always calculated problems. 18,000 times 0.89 to the 7th gives us $7,961. Let's round to the nearest dollar. 79.62. Notice if you had made the mistake where you forgot to take it off of 100 and you gave it 0.11 as our growth factor. Notice after 7 years, this says that our car is worth 0.35 cents, less than a penny. That's not necessarily realistic at all. That's a good indication you made a mistake in there somewhere. Anyway, that's a wrap for today's notes. I will see you guys soon.